the product lead for our quantum machine learning group at Quantinuum. I sit on the Cambridge quantum side of the business, and I'll sort of give you a quick introduction to Quantinuum itself. And yeah, it's really great to be here today. Thanks so much for having me, and hopefully you all enjoy the presentation that I have, and also the presentation from my colleague Justin, who is there in person. So what I'm going to start out with is just give you a quick introduction to the company, and then I'll dive into my exact presentation. So Quantinuum was formed late last year as a merger between Cambridge Quantum, which historically has been a quantum computing software company. It was founded back in 2014 as a spin out of the University of Cambridge. And then Cambridge Quantum merged with Honeywell Quantum Solutions, which was a business unit within the big conglomerate Honeywell that were building actual quantum computing hardware. And that's what Justin will be talking to you guys about today. So this merger of equal parts essentially formed the company Quantinuum, and this effectively has created the world's largest quantum company with a really global presence. In terms of our software areas of focus, what we're really building is enterprise quantum software. So this is a snapshot of our software stack. At the very heart of our software stack is our open source SDK and compiler Ticket. And Ticket is really what enables us to be hardware agnostic from a software perspective. So Ticket allows you to write your algorithms and compile them efficiently for any backend of your choice, whether it's, say, the IBM devices, the Honeywell devices, which are now our own Quantinuum devices, or any of the others that you see down below here. And so it's on top of Ticket where we build sort of user-friendly application frameworks or software products. And we have 5 main verticals of focus. We have a quantum chemistry team, quantum machine learning, and then simulation optimization. Our moonshot project, if you will, to use Google's terminology, is in quantum natural language processing. And then lastly, the most mature area of our company is in cybersecurity. And at the top here, you'll see these collaborative use cases. So one of the things that was part of our strategy very early on was we understood that we needed to work with industry on specific use cases to help them build out their quantum strategy and also build applications that really delivered value. And so that's what we're doing today. And this is a snapshot of some of the companies we've worked with. So now what I really want to talk about today is applied quantum computing for industry and really bridging the gap between classical and the quantum worlds. And the reason I want to talk about this is, as you guys all probably know, there's a ton of money flowing into the quantum industry. Last year in 2021, there was $1.3 billion of investment that flowed into the quantum industry. And along with this money, there's obviously a lot of talk of hype. There are overpromises, and this has been an expanding problem that a lot of journal publications have caught on to, a lot of industry users have caught on to, and this isn't a good look for the quantum industry in general. And what I really want to boil down here is try and answer the question of whether it is just hype or if there's something more at play here. So if you look back to 2018, the Washington Post ran this article. And in this article, they stated that the traveling salesman problem, which is a canonical example of an optimization problem, they said that this traveling salesman problem, it would take a ordinary laptop computer about 1,000 years to compute the most efficient route between 22 cities. And a quantum computer could do this within minutes and possibly seconds. Now, Bill Cook, who's a professor at the University of Waterloo now, and sort of the expert in tackling the traveling salesman problem, he tweeted directly at the Washington Post, said, to clarify, computing an optimal traveling salesman problem on 22 different cities takes 0.005 seconds on my iMac, not the 1,000 years. So why does this discrepancy exist? In another case, one of our competing hardware companies put this in an investor prospectus where they said a UPS driver on average makes about 135 deliveries daily. And to calculate the most optimal route for these deliveries, it would take a computer longer than the age of the universe. And I'm guessing UPS is probably not happy about the statement because they probably feel that they calculate the optimal route pretty well. So yeah, really, why does this huge discrepancy exist? And is it just hype? Maybe it is just hype, but in a lot of cases, I think the quantum computing industry is unaware of the classical state of the art. So if you look at these optimization problems, like the traveling salesman problem here, it would take a laptop computer 1,000 years to solve this problem if it was doing it in a brute force manner, if it was actually going to look at each possible route to analyze which one is the most optimal or most efficient. But classical algorithms are much smarter than that. And as Bill Cook said, he can solve this in 0.005 seconds, not in 1,000 years. So beyond just not knowing what the classical state of the art is, there are also a lot of unanswered questions when it comes to how quantum computing will scale. And one of the biggest unanswered questions is, what does the transition from classical to quantum look like, and how will it all integrate together? There are scaling problems at hand. We don't really know how quantum algorithms will scale. We don't really know how variational algorithms, which are the ones being employed predominantly today on the noisy intermediate scale devices that we have, the NISQ era devices. We don't exactly know how these algorithms will scale as the machines get bigger. We also don't know what hardware capabilities will be required for production scale implementations of some of these algorithms. So those are some of the scaling questions that we have. There's a general question in terms of what the crossover point may be between classical and quantum. So for example, what optimization problem sizes will be more efficient to be tackled using a classical heuristic versus a quantum heuristic? And for which problem sizes will that crossover point occur where you may want to shift to a quantum heuristic? And then the practical question here is, how will this crossover point be handled in practice? Will there be some automated way of shifting from a classical compute resource to a quantum compute resource? And then lastly, there are questions around hybrid workflows. So quantum computers, as we know them today, they're extremely good at tackling discrete variable problems, whereas classical computers, they are more efficient at tackling continuous variable problems. So how do we leverage the best of both worlds and combine the two in efficient hybrid workflows and potentially start to tackle industry's mixed variable problems where you have both discrete and continuous variables? So it's not all gloom and doom. It is getting better. Quantum companies are actively engaging in industry collaborations that allow and facilitate knowledge sharing. So we, as at Quantinuum, whenever we engage in industry collaborations, we treat those companies as subject matter experts in what they do. They are the classical experts, and we merely bring in the quantum expertise. So together kind of form this dream team where we get to learn from each other. Some companies are really getting focused on solving problems that are classically hard, but potentially quantum easy. And this is definitely sort of the areas of low-hanging fruit that we should be tackling today, rather than just saying quantum can solve all your problems. And then some companies, like the new Alphabet spinout, Sandbox AQ, are combining classical and quantum in their focus. So if you look at Sandbox, their focus is both classical AI as well as quantum computing. And they have formed a board of directors and advisors that consists of leaders in classical computing. And so this is definitely a very strong strategy going forward and tries to combine the best of both worlds. So what is it that we're doing at Quantinuum specifically? And today I just want to talk about two examples, one in optimization and the other in quantitative finance. And here I'll try and give you an idea of some of the things that we're working on to bridge this gap between the quantum and classical worlds. So in the optimization space, I talked about the traveling salesman problem, but I want to kind of build the intuition of why even look at quantum computing to tackle these problems. As Bill Cook mentioned, there are efficient classical heuristics to tackling, say, problems like the traveling salesman, but there are still limits to classical heuristics, although they're higher than what the quantum computing community generally thinks. There are problem sizes and problem complexities where these classical heuristics start to slow down. Whereas with quantum computers, you can leverage quantum properties to actually develop and design novel heuristics and heuristics that are fundamentally novel in how they work. So these quantum heuristics, they're hypothesized to be able to explore complex energy landscapes much more efficiently and being able to converge to better quality solutions, which at the end of the day for companies, if they can tackle an optimization problem better, converge to a better solution, this could lead to significant economic savings. So what are we doing specifically at Quantinuum? What we're trying to do today is really push the state of the art in terms of developing better variational quantum algorithms. And then we are starting to benchmark these against classical heuristics and trying to outperform, even the most naive classical heuristics today and work our way up to the best classical heuristics that exist. With these quantum algorithms, we're studying convergence and scaling properties in terms of, how will these perform on larger problem sizes, as well as on larger hardware. We're also researching sort of fault-tolerant approaches. So these are methods for kind of fault-tolerant quantum computers, which may come down the road in say, a few years' time. And we're comparing, how variational algorithms might scale versus some of these fault-tolerant algorithms. And we're starting to also develop ideas in-house for how we can tackle mixed integer problems, where we're not only just tackling discrete variables, which is what quantum computers are traditionally good at, but also looking at incorporating continuous variables into the problems. So what does this unlock for industry? One of the things that I think I've been seeing as a trend when it comes to talking about the potential for quantum computing in tackling optimization problems, industry can start to think about large-scale problems that they have never tackled, but they want to. So what we're working with companies on is, okay, hey, what are some of these problems that you ideally want to tackle, but have been so large that you've never thought to even formulate them fully? And so we work with them as to formulate these problems. And then once we've sort of formulated the global scale version of this problem, we then work to create a reduced sized version of this problem that we can tackle on the hardware that we have available today. And then we work with these companies to actually develop sort of bespoke quantum algorithms to tackle these problems and really evaluate their performance and project how these algorithms might scale going forward. So some of the specific work that we've done at Cambridge Quantum has been to develop this algorithm known as the filtering VQE algorithm. And we released this in the summer of last year. Specifically, what this algorithm accomplishes is two main things. It showcases much faster convergence and up to 100 times faster convergence than existing quantum algorithms today. So we're really pushing the state of the art in terms of what quantum algorithms can achieve for tackling optimization problems. And then the second thing that that this algorithm achieves is much more powerful scaling. So we have developed methods in-house known as causal cones, which allow us to scale the algorithm to tackle larger problem sizes on a limited number of qubits. So what these causal cones allow us to do is take up a full sort of energy Hamiltonian and split it up into chunks. And then we can look at the very few qubits that really affect the energy Hamiltonian of that specific chunk. And this allows us to effectively parallelize this problem and tackle it using much fewer qubits. So for example, we can now tackle, say, a 23 variable problem, not more than 6 qubits, and most of the time we were really using only 4 qubits. And sort of before this work came out, you needed sort of 1 qubit for every variable in your optimization problem. So if you had this 23 variable problem, you would need 23 qubits to solve it. So that brings me to how we actually work with industry. So in one of the applications we looked at with a company called Nippon Steel, who are one of the largest steel manufacturers in the world, was this job shop scheduling optimization problem. So you can imagine that Nippon Steel has their factory floor with a bunch of different machines on it, and they need to schedule jobs in specific orders on those machines to end up creating specific steel products. And so this is an NP-hard problem for them, something that scales terribly. It scales exponentially with the number of machines and number of jobs you may have to schedule. And so we worked with them to actually, formulate their problem in such a way that it can be tackled with a quantum computer. And we worked with them to develop this FVQE algorithm and apply it to their problem. And what we were able to showcase through real hardware experiments is that our algorithm actually does scale nicely, especially as you start to run it on larger and larger problem sizes and larger variable or qubit counts. So in this graphic that you see down below here, what you'll see is as we reach to about 23 qubits, we do start to see the effects of noise. But hopefully, as the hardware matures, these algorithms will still continue to scale nicely and converge to the most optimal solution. And then if you look at this bottom right-hand graph here, what we're able to show is, we can actually sample the ground state, which corresponds to the most optimal solution of this optimization problem. And we can sample it at a rate of 25%, which is incredibly good because, if you sample this optimal solution or ground state just once, you will have converged to your optimal solution. So sampling it 25% of the time is a great result. So obviously what we want to do is scale this to the order of actually being able to tackle problem sizes in hundreds and thousands of variables in size. So that's where obviously we're waiting for the hardware to be able to do this, but also we need to really improve these variational algorithms to look at how they may efficiently scale. One of the other projects that we recently worked on was with Deutsche Bahn, which is the world's largest railway company, and it was on a train scheduling optimization. And so this is an example of how companies are starting to think about a problem so large that they've never thought about it before. So Deutsche Bahn has this vision of the world in 2035, where in all of Europe, there will be a fully automated digital rail network. And so in this worldview, they are trying to integrate quite a few of the leading technologies from computer vision to reinforcement learning, 5G, robotics, and as well as quantum. And so their end goal here is to have fully autonomous trains that can, optimize their schedules autonomously. They can know when to brake, know when to speed up, and effectively, they want to be able to do this across the entirety of Europe. So what we did with Deutsche Bahn in our research collaboration is to really figure out what domain-specific knowledge we could take from them in terms of this train scheduling problem, and how that domain-specific knowledge could contribute in advancing the field of quantum computing. So we looked at, what sorts of problem formulations can we come up with that are super innovative, that are resource efficient, and really well suited for some quantum algorithms that exist today, especially our filtering VQE algorithm. Then we worked with them to iteratively improve our FVQE algorithm, especially trying to scale it from, say, a small problem size to larger problem sizes. And then we mapped out, what white spaces still exist for future R&D. So this collaboration was hugely exciting for us, because I think we got to learn as much from Deutsche Bahn as they did from us. So Deutsche Bahn came out of this with knowing how to run our FVQE algorithm, knowing how to build quantum circuits and actually execute them efficiently. But we came out of this project really understanding sort of some key aspects of train scheduling optimization and how to be innovative in our problem formulations. And we learned from the operational researchers that existed at Deutsche Bahn. Okay, so that's enough of optimization. Now I'm going to talk about another application area in quantitative finance, and specifically I will focus on Monte Carlo simulations. So here again, why are we thinking about quantum here? So Monte Carlo simulations are the workhorse for pricing a lot of financial instruments, and Monte Carlo simulations also extend to engineering applications and physics applications as well. But Monte Carlo in general consists of three very simple steps. You typically just sample from some probability distribution of interest. Then you would perform some deterministic computation on the samples. And then you really just average the results to obtain some expectation value. Now, this is an extremely computationally intensive task, and you need to obtain a ton of samples to really obtain accurate estimates or accurate expectation values. With quantum Monte Carlo integration has what they call a guaranteed quadratic speedup that's theoretically proven, and it's through the use of this quantum amplitude estimation algorithm. And so essentially what this quadratic speedup means is that if classically you needed n number of samples to obtain some precision value, quantumly you would need square root as many samples, right? And so this means that instead of having a runtime of t classically, quantumly you would have a runtime of square root of t. And this has huge implications for financial institutions who are running these Monte Carlo models definitely overnight and sometimes over multiple days. So with using quantum Monte Carlo models, what they would be able to achieve is being able to run things in near real time that they were running overnight today. And the things that they were running over multiple days could be run in overnight. Now, that's all well and good. The downside here is that quantum Monte Carlo has been unrealized in practice. And this is because the algorithms require extremely deep circuits, and the depth of these circuits are so large that they're easily overwhelmed by noise, especially in this NISQ era. So your algorithms never converge, and so this quadratic speedup, although theoretically proven, is wholly unrealized. So what we're doing at, actually, let me take a step back here. So one of the interesting collaborations that has come out in this space has been between Goldman Sachs and IBM. And the reason this some of their work is hugely interesting is because they are asking the hard questions in terms of trying to quantify the exact quantum resources that will be needed to implement quantum Monte Carlo at a production scale for pricing financial instruments of interest to Goldman Sachs. So here, some of the things that they looked at in these two papers is the calculation of derivative pricings, as well as what they call Greeks, which are essentially derivatives of derivatives. And what they looked at trying to quantify here is not only, how many number of logical qubits will we need to price these products, but also what fidelity will be needed, and that corresponds to the depth of circuits that you will need to run, as well as what sorts of speeds will we require, wall clock times will we require to actually price these products at a realistic time scale. So say you want to price a product within 1 second. For a lot of these applications, you will need speeds that we don't have today. So this is great work, because now we get to understand, what sorts of hardware requirements will be needed to actually run these at a production scale. And so what we're doing at Quantinuum is trying to design better algorithms that start to decrease the hardware requirements that you may need. So last year we released a new quantum Monte Carlo algorithm that essentially what it does is it shows that any Monte Carlo algorithm can be decomposed as a Fourier series. And if you do this Fourier decomposition, you actually need much shallower circuits to implement your quantum Monte Carlo algorithm. And it still achieves the full quadratic speedup. And so this is an algorithm that would be runnable on the NISQ era devices in the next few years. And so specifically what we were able to show is that for the financial instruments of interest to banks, and specifically the ones mentioned in the papers from Goldman, we can reduce the hardware resource requirements by up to 90%, which is a significant advantage and greatly accelerates sort of the timeline to obtaining a quantum advantage. And so we think, based on our resource estimates and also based on the hardware roadmaps published by the likes of IBM as well as ourselves, that we can find a quantum advantage within the next 3 to 5 years using our quantum Monte Carlo algorithm. And so that's hugely exciting. And so what we're doing in client collaborations, unfortunately I can't dive into specifics here, but we're really trying to develop an enterprise grade quantum Monte Carlo engine by really understanding what's of interest to organizations, whether it's banks, insurance companies.
I know, let me just shut off the my little speaker here. I was listening.
Okay, I'll keep going here. For example, some oil and gas companies that may be interested in energy trading. So specifically what we want to learn from these institutions is what probability distributions are of interest to them, and really what that means is what data are they interested in. And this obviously forms the distributions that we would draw our samples from in our Monte Carlo engine. And then we also want to understand what sorts of functions and computations they would like to perform on these samples. What products do they want to price, and how do they potentially want to calculate, say, a value at risk. And then lastly, we also want to understand, much like what Goldman Sachs and IBM did, what expectations for production scale implementation are. These could be things like time to price a specific instrument. It could be, the size of your problem or the size of your portfolio. And also things like, what does a realistic model complexity look like? A lot of things that we see in the quantum literature are proof of concept demonstrations on extremely simplistic problem complexities that would never meet the expectations of some of these leading banks. And so we really want to understand what these realistic expectations are in terms of complexity as well. So this brings me close to the end of my presentation here, and maybe just the last few words geared towards you all in academia and you all as you're thinking about starting your careers. And so really I want to kind of spell out what, from my perspective, the talent that we as the quantum industry need. And so obviously we need quantum information scientists. That's a no-brainer. There's a general lack of quantum computing expertise, and the demand for this far exceeds the supply. But we also need, experts in their respective classical domains who do understand quantum algorithms and who can help us sort of bridge the gap between classical and quantum. And I think this is going to be, perhaps even a bigger need than the need for pure quantum experts. And then lastly, we also need, people who are client-facing, but with rigorous technical depth to be able to tease out, some of these industry pain points to help companies formulate their problems in a way they've never done before, and really map these problems to quantum solutions and be able to describe specific business value to clients. Because that's the only way we're going to convince industry to actually work with us and start developing methods and algorithms before we have any sort of realistic quantum advantage. Okay, I think I whipped through that. So I'm going to pause here and see if you guys have any questions for me.
Hi, Anand. This is Rahul here. I know we talked briefly over LinkedIn. So I think my question is answered. I was looking into algorithms where doing a simulation on drive-ups, probably like Uber Eats. So the problem here is you have these shoppers who shop for a retailer, you place an order, and we want to, the question here is to expand to new markets, but that costs, expanding into new markets will have a potential cost to it. And there is a classical algorithm we are using already to do a simulation to determine the cost for expanding into new markets. The question is, can I take help of quantum to, like leverage on the classical algorithm of prediction here for those drive-up simulations?
Sure. So I guess to clarify, is this a sort of prediction problem or sort of a brute force optimization problem?
An optimization problem.
Okay. So I mean, in general, like I mentioned in my presentation, there's a lot of hope for these quantum heuristics to be able to tackle these sort of large scale optimization problems. But to be completely transparent, there's not a single quantum heuristic that exists today that outperforms a classical heuristic, right? Okay. So it really depends on the business value and the time scale that the organization might face. So for example, if Uber is trying to solve this problem today, it wouldn't make sense to try and implement a quantum solution because one, it wouldn't be able to tackle the scale of problems of relevance to Uber today, and nor would it outperform existing classical algorithms. But the goal is to be able to start developing these research efforts to look at some of these problems that may scale terribly from a classical perspective, but that may scale favorably from a quantum perspective. And so that's what I would recommend really, is like if say Uber did have some R&D budget that they wanted to spend with the hope of developing some quantum algorithms that would provide a ton of economic value to them down the road, then this would definitely be something to investigate.
Sure, thanks. And a second follow-up question, when you say about these algorithms that you're developing, so I believe these algorithms are not open source, and we have to work with Quantinuum to take advantage of these algorithms, right? When you say you develop the quantum Monte Carlo simulations and other algorithms.
Yeah, definitely. I mean, one of the big things, as you can imagine, for a company like us is the value of our intellectual property. So some of the algorithms that we develop there that we think are cutting edge, we would obviously try and seek to protect them. What we have made open source is our SDK and compiler ticket, which is the framework upon which you can build your quantum algorithms. And so that's completely open source, and you can start to use that. But no, you're exactly right. Some of these algorithms that we have developed are not open sourced.
Thanks. Thank you, Anand.
Yeah, a question. Like, can you hear him, Anand?
Faintly, but yes.
Let me just pass the computer.
Hi, Anand. I was wondering like how an iteration of like quantum Monte Carlo sampling like would differ from like a classical iteration. Like, in the classical sense, you have like some probability distribution that sample like, whatever branch or whatever is most interesting, like has a like most entropy or whatever, least entropy. But like, how does that differ in like the quantum one? Do you build like some sort of superposition, or how does that work?
Yeah, exactly. So you would take your probability distribution of interest and you would translate it into a quantum state, basically in superposition, and then through amplitude estimation, you would sort of evolve the algorithm to converge to a specific, most likely amplitude.
Okay, cool. Makes sense. Thanks.
Yeah, and so there, the quadratic speedup really comes in because you're on the quantum side, you're working directly with amplitudes, which are the square root of probability, whereas classically you would be working directly with the probabilities themselves.
I see. Okay. Thank you.
Any other questions?
Barry, I see, has a hand up.
Yeah, I just was by amplitude amplification. Do you mean Grover's algorithm or something more exotic?
It's a version of Grover's algorithm. That's sort of the base of it. Yeah.
Okay.
Mm-hmm.
Thank you.
Yeah, absolutely.
So I guess if I can ask one more word, that
Oops, sorry, Barry, you've cut off.
that means then that they're, oh, can you, it says my connection is unstable. I'll put it in the chat.
Okay, perfect. Yeah, exactly right, Barry. There is definitely a practical use for Grover's. It does depend on the depth of circuits, but yeah, some of the things that we're trying to do is really limit the size of the circuits that you need, and in a lot of these problem areas, the quantum advantage really depends on the specific instance of the problem, and so that's where we kind of need the help of industry to formulate these problems and really look at, for which ones will perhaps quantum advantage come first and for which ones will they come later. And, based on certain problem instances, are there characteristics of the problem that we can leverage to design better algorithms and potentially design algorithms that require shallower circuits?
Okay, I think that's all of the questions for you, Anand. If there's any follow-up, you can either send that in the Slack or email me at that's@berkeley.edu. And
Awesome.
Justin, you want to take over the baton?
Thank you.
Okay. Is it possible to mute that mic?
Yes.
Okay, another test of the audio. Suppose I should try and start a video. All right. A little bit of an awkward angle, but it's all right. Okay, great. Okay, great. And then is the slides showing up for people on Zoom? Okay, great. Well, this is pretty fun because we get to go from like all the way the world of financial instruments down to controlling single atoms to actually make the quantum computers possible. So I'll talk for a few minutes now on about the hardware that we have as a part of Quantinuum, based on using single trapped ions as qubits. So we had a good intro to kind of what Quantinuum was. I wanted to talk a little bit about my background. I I kind of started doing a PhD in atomic physics at the University of Colorado. And the focus of the research was really controlling atoms and introducing entanglement for enhancing precision measurements. And so this was, actually where we would shine light on an ensemble of atoms and do a measurement that gave you some information about the quantum noise, but then preserved the sensitivity to things that you would want to measure, like for atomic clocks or gravitational sensors, that kind of thing. I then went to the National Institute of Standards and Technology in Boulder, Colorado, where they kind of have a long history of using trapped ions for doing measurements in clocks. And there I was a part of a team that built a kind of a novel sort of ion trap that would produce these 2D arrays of ions, and we could introduce entanglement in them for doing quantum simulations. So that's like a picture that we took of an ion crystal. I think that one was probably around 70 or 80. Each one of those like smears is a single trapped ion. And then in 2017, I started at Quantinuum, which at the time was Honeywell Quantum Solutions, and mainly focused on the design and launch of the system model H1 quantum processors. So this is kind of a cool image of like when we first had the first ion trap in the system, and the image is coming from like sweeping a laser beam across the surface and then capturing the light that was scattered off it to see it for the first time. So as you can imagine from this background, like my favorite kind of qubit is going to be one that we make out of single atomic systems. And in this case, really, at Quantinuum, what we've been using is the ytterbium-171 ion. And in particular, we're using qubits in the electronic states. So that could be in some, in some trapped ion work, it's using the orbitals like the s or p orbital states of the electron as the qubit. And we definitely use those states, but we actually store the quantum information, what's known as the hyperfine level. So in the single s orbital of an ion, there's actually an interaction between the spin or the magnetic moment of the electron and the spin of the nucleus. And that actually forms like this multi-level structure, and we can have a quantum state 0 and 1 just in that s orbital. And storing the information there has some really nice properties. Like one of them is just that the lifetime of that one state is very, very long. And so we basically have great kind of coherence for either quantum state of our qubit. The other thing is that by exciting the electron to the p orbital or the d orbital, you can actually interact with light. So we can use lasers to control the state of our qubit. It's kind of another nice tool in the toolbox. Of course, each atom is guaranteed by nature to be identical, so we don't have to worry about qubits changing. Each one is identical from the get-go. And the other thing is a lot of the error sources with our qubits are really well known. Like, the theories of quantum physics and atomic physics are some of the best tested, and we really understand the error sources, whether it's, the limitations to the lifetime in the ground state, or how scattering of photons when we interact with these other orbital states cause errors. We understand them really well. And so our job then is into capturing and controlling these single atoms and manipulating them, meaning, using laser light to initialize them into pure quantum states, setting up the environment so that we protect them from other sources of decoherence, reading out the qubit states, and actually setting up the gates. We have a great toolkit for doing all of this. This is a picture of Juan Pino, who's kind of like my counterpart, another manager at Quantinuum with his quantum tool belt ready to go. We get to use a ton of tools that have been built up for many years in atomic physics, developing precision measurements like atomic clocks. So, since the 1950s, atomic clocks have been kind of the standards for, industrial, they're on satellites, a long history of building up the toolkit. So I'm going to just kind of talk briefly about a few of those and then go into detail about some of what makes our trapped ion quantum computers special. Okay, ion traps is a big one. So this is an image from 1991. I don't know if you've seen this before, but the idea is that you can trap ions in this kind of configuration where you have 4 metal rods. Each of them have an alternating voltage on them. And then these end capped electrodes kind of hold the ions there, and you can form these nice, either you can trap single ions, you can form linear chains, you can trap like big ensembles of them. So we have ion traps for kind of isolating single atomic ions is the first step. We need to maintain an environment, as like I said, for coherence. So one of those is just, we need to have an ultra high vacuum environment where you don't have other, particles kind of bombarding these ions, bumping into them, which would cause, shifts in the energy levels. So we have ultra high vacuum environments, this is a picture of one of our chambers. Part of that is also a really low noise magnetic field environment. So one of the few kinds of fields that couple to our qubit and would cause errors are magnetic fields. And so that kind of goes into this as well. And then lasers is the other big component. So, not only do we use the lasers for manipulating the quantum state, but, unlike in other kind of qubits where you rely on physically cooling the qubits down with like having them be in thermal contact with something like, liquid helium or dilution refrigerator, here we can actually use lasers to cool these chains of ions that are being levitated in the trap. So we prepare the ions' motional state and their quantum state with the lasers. We read out the state of the atoms by, again, shining a laser light on them. And depending on the qubit state, they'll either shine like a star that we can collect that fluorescence, turn it into digital signals, and we'll see a bunch of counts on a digital pulse counter if the ion is in one state, and you'll basically see nothing if it's in the other state. So we use it for readout. And then you can also use it for gates, which is really nice because essentially what you can have is 2 ions in the same trap, and the quantum information basically they don't talk to each other at all. Their electron states, they don't feel at all. But then you can kind of instantaneously turn on a laser field, which generates a force on the ion that depends on its quantum state. And then the Coulomb interaction can transmit that force to the other ion in the trap. So you basically have this very strong force that you can turn on depending on the quantum state between the 2 particles in the trap just by flipping on and off a laser light, which means you just can go from a totally isolated kind of qubit to one that has really strong coupling for the gate and then turn it back off again and be in a mode where you're preserving coherence.
Excuse me.
So what our systems look like physically is a little bit like this. A big chunk of it, you have the kind of the person there for scale, but a big chunk of it is the laser sources and then the optoelectronics that you use for conditioning these signals. And then that's kind of brought up with optical fibers close to the trap. And we have another set of like these optics to direct it into that vacuum chamber that I was showing earlier. We have basically a microscope kind of positioned below the chamber that's collecting the light from the ions so you can do the state detection, and then a ton of control electronics that are giving us control over all this, as well as receiving the programs from the user there up at the top. So the user submits a program in kind of a agnostic assembly language that gets translated into pulse sequences that are custom made for our ion traps, and then we send the results back up to them. So I really skimmed over a ton of interesting details there, but because what I wanted to talk a little bit was, okay, how do you really envision going to a large scale quantum computer with this technology? This was sort of an image from 30 years ago, and these are like macroscopic kind of traps. And the idea is that we're going to take advantage of microfabrication to make a whole bunch of these on one device. So this is a picture of the ion trap that's in the H series quantum computers. It's what's known as a surface electrode trap. And it's basically just a single 2D surface with a pattern of little gold pads all across the top that we can individually control all the voltages on. And what it means is that we can have a whole bunch of those ion traps miniaturized and kind of manufactured all across the surface. And so this device can do something like the equivalent of 20 of these traps that I was showing, all on this one device and all in parallel. And then you can vary those voltages on each of those little pads to send ions all through the device and kind of connect all of these different traps. So you can have quantum gates between two ions in one trap, and then send that information across the device to have them interact later on. And we can do those moves with really high fidelity, allowing you to actually, construct for these NISC era devices like some of the deepest circuits that you can run today. So this idea is not new. It's been around for a long time, as proposed by a group at NIST, and it was what's known as the quantum CCD architecture. And so, but we've been one of the first groups to actually put all these pieces together in a device. And it's actually like, I don't know, it's really cool that it's online and people can access this and use it for themselves. So, the basic idea is the ions are the qubits, and you have this microfabricated device where you have different specialized zones for the different operations. And then you can physically transport the ions around to get them to the operations where they need to be. And you can keep your qubits isolated when they need to for high fidelity operations, or operations that don't have crosstalk and affect other parts of the device. Okay, yeah, I mentioned this is sometimes known as the QCCD architecture, and I might say that once or twice. Okay, so a few more of the details about how our system works. One of the key components is that not only do we have ytterbium-171 ions as our qubits, but each ytterbium has a barium ion kind of buddy that follows it everywhere around in the trap. And what that means is after you do some of these moves and these transport operations, you will induce some excitation into the motional modes of the qubits. And that would actually reduce the fidelity of your gates. Because, again, I kind of mentioned the gates depend on this Coulomb interaction force between the ions. And if there's other kind of excitation in that mode because of this motion, it's going to impact the fidelity of that operation. But what we can do with the barium ions there is apply laser light that only affects those and cools them down. And the quantum information stored in the ytterbiums is protected. So before each one of these 2-qubit gates, we can recool the system down through the barium ions. And that's oftentimes called sympathetic cooling, and ensuring we just have the highest fidelity operations that we can. Let's see, I do see a hand raised here. Maybe I could answer a question quickly.
Yes, I have a question. Can you hear me?
Do you want to speak up?
Yeah, I tried to speak up. Can you hear me?
I'll keep going, and then maybe it'll show up in the chat. Okay, so here's kind of a.
He actually posted it. He said, "How you leave the quantum state without destroying it."
You do project the quantum state out of a superposition, but I'll actually get to one kind of nice feature of this architecture soon. But I guess it's worth pointing out, you do project the quantum state out of any kind of superposition, but the ion does remain in the trap, because you actually can leave the ion in place and just collect the photons that are being scattered off of it. So that's kind of an important, sometimes if you've worked with ions, sometimes it really means you send them into some kind of ion detector to detect what state they're in. And we don't do that here. Okay, so this is a closer up picture, and it's kind of colored to give you an indication of how we have specialized zones in this architecture. In particular, the blue ones are what we call our gate zones. And the center 3 right now are the ones that are set up for doing 2-qubit gates. Another special zone is all the way on the far right side, is actually what we call the loading zone, where I'll show you an animation in a minute that gives the idea of how ions actually get in the trap. Then in this architecture, we kind of put those 4-ion crystals through the device. In the original 10-qubit configuration, they tended to all hang out in the gate zones. And there you can kind of do the splitting and combining of the 4-ion crystals so that you could isolate just a single qubit for measurement or single qubit gates, and then also recombine them and cool them to do 2-qubit gates. Now, of course, another transport move that you need to be able to do is what we call a swap, where you do this rigid rotation of the crystal to get one of the qubits past the other one, so then it can slide down and interact with other parts of the device. when you go to do gates, we actually have a series of parallel cross laser beams that go into the center 3 gate zones. And I'm kind of highlighting this because sometimes people will say, well, trapped ion quantum computers can't do gates in parallel. And so one of the things that we've sort of pioneered here is just the optics setup to be able to do 3 gate zones in parallel. And as maybe suggested by the blue coloring, it's like we have plans to do more zones in parallel. So that's one of the things that can actually help us speed up the device as we start packing more and more qubits here. The other thing is this picture is out of date because now the kind of state-of-the-art H1-2 device uses 12 qubits. And so there should be like another 4-ion crystal in here somewhere. And it's kind of another, the way that we've been able to grow the capabilities of the system is keep the same ion trap in place and modify just the voltage waveforms to build in more and more of these ion traps on the kind of the same chip. Okay, a few more. Yeah, this is our fun animation. I kind of mentioned loading the trap. There's actually that zone that has a hole in it, and we have a beam of neutral atoms that pass through the hole. Then you can shine a laser light that actually ionizes it and pulls off an electron. That means the voltages can actually hold on to the charged particle and kind of form this little potential well. And now by trapping on it. So then by affecting the voltages on those smaller patch electrodes, you can kind of slide this potential up and down the device. And this is showing like the idea is you can move it to a special zone where the qubit's by itself and perform this as like a Hadamard gate operation. And then when you need to do a 2-qubit gate, you can merge these 2 wells together. So now the ions are in the same trap and can be really tightly coupled for actually performing the 2-qubit gate. And then afterwards separate them again and send them to other parts of the trap for measurement or interacting with another ion. So maybe, to try to make the connection too of how this works in the typical like circuit model picture of a program. Here, it's just like kind of a dummy example with 3 qubits that are labeled by their colors. So to start out with, we have to initialize each one in the quantum, the 0 state. So up at the top on that time chart, we're going to like move through the circuit left to right by going from top to bottom on the ion trap picture. So we can just we have beams to initialize the quantum state of all 3 ions at the same time. And then, fortunately enough, when we go to do the Hadamard gate, those 2 qubits are already sitting in the gate zone. So then the next step is we want to perform a 2-qubit gate between red and green. But this is where our compiler has to step in because what you do is send in the circuit, and then our compiler has to make a choice of how it's going to try to move these ions most efficiently through the trap. So before we get to the 2-qubit gate, we actually have a move and merge operation happening. These 2 qubits go into the same well. And now we can have the lasers flash on for the 2-qubit gate. But of course, now we need to slide the red qubit past the green so that it can get over to do the 2-qubit gate with the blue. So that's that move operation. And we have lasers in that second zone to form that gate. And then the last operation we have is measurement on the green qubit. As I kind of mentioned, when we go and do the laser operation, it's a focused beam that's just addressing that single qubit. So while you do collapse the quantum state on the green ion, the coherence in the rest of the register is preserved. And that's like actually a pretty important operation, especially for looking at error correcting codes, moving towards fault tolerant quantum computers. And maybe I'll say that's one of the reasons that we really wanted to pursue this architecture for our quantum computers is because we wanted to make progress down the road towards doing research in error correcting codes, which we know we need to get to in the long term for some of the most important applications. I see a question.
So each operation, you have some error. On the right side, where is the most likely stage for you to get error for each operation? Is it the shining of the lasers, the swapping, the splitting, the moving?
Right now, the laser operations are the highest error in our device. We did like a comparison. In particular, you can do this physical swap operation, but you could also do a series of 2-qubit gates. And the error in the physical swap is at least 1,000 times lower than doing the 2-qubit gates. So this classical just moving the ions through the device, it seems like we're doing really well on those operations. And that's a big advantage, I think, when we go to do some of the algorithms, because devices where you have to do the 2-qubit gate swapping to get information close together, we get to save like a lot of those gates, or effectively have lower error.
Yeah, I was gonna ask about that. Is that because the barium essentially, like, you can do sympathetic cooling and like your movement essentially doesn't add any additional quanta?
That's right. The additional heating that's added by the transport is pretty low, and it's definitely low enough that we can recool it out with sympathetic cooling pretty efficiently.
I guess I imagine that is like longer though. So is there like an assumption that maybe in the future you can get the 2-qubit gate up like errors down, and then you would save, I guess?
Yeah, I mean, given, so some of the tests that we ran is we would basically try to do more and more of these swap operations and look for a time when it failed to move the qubit. And I think we got up to the point where we were doing like 1 million and still not seeing a single error. And we started to say, like, I think it's going to be pretty hard to approach 2-qubit gates in the way we currently are that's going to have that good of fidelity. So what we do need to do is figure out how to recool faster to speed up the device, and continue to be able to do some of those transport operations with less and less excitation as well. This could be smarter about recognizing, okay, if you've only done maybe 3 or 4 swaps, you actually don't need to recool before doing the gate and save that time. Oh yeah, we have some cool pictures of, so these are using that microscope, some images of the ions actually in the trap. So on the top is kind of showing this split and combine operation. The 2 circles in real space are about 200 microns apart. And it's just showing having 2 separate ions, bringing them very close, merging them into a single well that gets brighter, and then like splitting them back apart. And then at the bottom is showing kind of the movie of doing that swap rotation operation. You can kind of see them individually together, and then as they do this rigid rotation, they get a bit brighter and smeared out, but kind of completing the move. I think, so you were kind of asking about error sources, and maybe sounded like you were saying in different locations. So this is some data from the current machine. We have 12 qubits, and I kind of actually broke out average fidelity of the operations by zone. And you can see that, we're typically able to do operations pretty similarly across the device. And I don't know, like, these are typically benchmarked with like randomized benchmarking techniques, where you kind of basically repeat the operation many times with certain random variables and look for a decay in the final state coming out. And yeah, I think on a component basis, there's some we're able to achieve some of the highest performance of any processors out there. And I think it's really just attributed to this properties of trapped ions, where the qubits are perfect, they're identical. We have really great isolation. You can snap on lasers to kind of control them, and we have a lot of great techniques to do this. So this is where I was going to pause and actually try and talk to the machine here with just like a super simple circuit. So we'll see how this all works out. Screen sharing has stopped. Okay, I don't want to do that. Right. Okay. So this is just a super simple circuit, but the idea is to kind of show a little bit of what ticket looks like. Here I'm accessing it with Python and the PyTicket package. So I'm kind of importing the circuit object. And then, you also have to connect to a backend. So we'll connect to the Quantinuum backend. And so first I'm just going to talk to the emulator and see kind of what state that's in, make sure I'm online. Yep, so that's showing we're connecting to the -1 emulator. It's 12 qubits. So now let's try and talk to the actual machine. And that shows us online. So let's go for it. I am just doing a basic entangling gate to make a bell state here. So yeah, about as simple as it gets. I'm gonna try and play it safe and only do 100 shots. So I've just submitted, those 2 operations with the process circuit command. And then, normally if you were kind of doing this, for your job, you'd set up some kind of asynchronous like check on the status regularly, because typically your circuits go into some kind of queue with all the other users. You have to wait for the results to come back. Maybe you'd set it up to wait overnight. In this case, we actually got a reservation for the machine for this. So our results are ready right away. Let's see what it says. Okay, so what I did first was just showing like, we're just looking at the results for qubit 0. And, as you can imagine, it's sitting in some superposition state of 0 and 1. And so we get kind of a 50-50 mix of the 0 and 1 state. This is looking at the first 30 results for just that qubit. So that looks totally mixed, but then of course the idea is that if we've actually formed an entangled state, we should see perfect correlations between the 2 qubits. And so that's what we're looking at here. The first 20 results, was it perfect? Yeah, so that's great. So then this is actually just plotting. Oh, okay, no, in the full sample, we had one time where we got a result back that they weren't perfectly correlated. But so that's great. I got the biggest smile on my face that we like actually connected to the machine and did this. I just want to do it once with 1,000 quick. Okay, so now you can see it's the circuit's in the queue and it was done already. That's so awesome. That's so awesome. Yeah, oh man, it's so beautiful. Like 501, 499. And let's see how I did on all 1,000 here. Yeah, okay, so this is like right at what we'd expect. So when you take into account the measurement error for looking at 2 qubits and the measurement error for the single 2-qubit gate, and you kind of just do the multiplication, you get right at about 90% of what you'd expect. So, I'm pretty happy with that. So the other idea was that, we don't have to stop at just entangling 2 qubits. Like, let's just entangle them all in the whole device. So this circuit is, we're just going to kind of go through a ladder. We'll do a single Hadamard and then a ladder of C0 gates to generate what's called a GHZ state, where it's, in the end, all the qubits, we should either find them all up or all down and nothing in between. So this circuit has 11 gates, and we'll do 1,000 shots of that. This one should also be super fast. This is like a very typical, like, when we were first bringing the device online and we wanted to see, like, do we think this thing is working? Do we think it's like doing what it should be? This is one of the first circuits because it's, it's pretty nice to see all the qubits are entangled. Okay, now we actually got the running message, so that's kind of fun. Okay, we're ready. And yeah, so that's our GHZ state there. And we're hitting that, all of them perfectly correlated, 90% of the time. Yes. Thanks, I appreciate that. All right. Okay, I just got to get my slides running again here. Okay. Now, we quickly found out that just doing those like component benchmarks is not enough for understanding how your system's going to perform as like in full circuits. And so this is why we really have liked using the quantum volume benchmark, because we feel like it has this kind of, it's like a very hard stress test of the system. So I don't know how much you've heard about like quantum volume as a benchmark. It has these really big numbers on it, but what it's really telling you is basically what is the largest square circuit that your device can successfully run, where the sides of the square are, number of qubits on the y-axis, and then kind of the depth of the circuit on the x-axis. And where depth in this case is, each step of depth corresponds to some random pairing of the qubits and doing 2 qubit gates, or really a random SU4 unitary operation on each of those 2 qubits. So what the circuit looks like in our device is, we start with an initial pairing, do the operations, and then you have to do some big transport dance to randomly pair different qubits together. And so you do that n times for whatever level of the test that you're trying to pass. And then we have some measurement that you read out. And you do basically some classical computation to look at what state you would expect and kind of pull out an answer of how well you did. And the details of all that, because it is a little bit more complicated in the references there. And then of course, that's just like one instance. And so you have to do then many randomizations and make sure you get the correct answer above some passing threshold, within some confidence bound. So this is the data from the latest successful benchmark. Is like a couple weeks ago, I think we published passing the quantum volume for 12 qubits. And it sort of shows, like, as we did more and more random instances, you kind of see that on average, the confidence band shrinks, and then we can show, okay, we're above the passing threshold on these 12 by 12 circuits, within a 99% confidence interval. And so that's what's known as like, okay, this device has like passed that benchmark. And as you can imagine, because you have to do quite a few 2 qubit gates, I think each SU4 for us, is 3 2 qubit gates. So that's kind of like a depth of 30. And then you have to do all of these transport operations. It kind of just really gave us a nice test for kind of the circuit at large. And so we've tracked this metric over like 3 devices now and 3 different labs. We started with what we called the H0 device that had 6 qubits and have kind of been able to steadily increase on this track. It is really a combination of, first, we just had to get more qubits, right? Because once you hit 6 by 6, then you have to add more to the device. And so that mostly some amount of work in building those voltage waveforms for creating more of the traps on the surface trap. There's real hardware upgrades. Like, one of the things we had to do is like pull out the microscope and insert a new one to kind of keep advancing the quantum volume. We changed to a lower noise set of electronics, so we had a less electrical noise affecting the gates. And then there's been a number of what I call like software improvements, where teams have gone in and done studies of what is the exact right sequence of laser pulses to cool down the ions before doing the 2 qubit gates, and seen boost in gate fidelities from doing that kind of work as well. So yeah, it's really been fun. Okay, but one of the problems with quantum volume as a benchmark is it actually leaves out a really crucial component of how the device would perform for error correction. And that's kind of the measurement and being able to respond to measurements to correct errors. And so I wanted to talk about that a little bit as well, because quantum volume just completely misses that point. You only ever do a measurement at the end. So I kind of touched, I mentioned this already, but by doing this, the ability to isolate the ions means that you can preserve the coherence otherwise, and the device is great. And we've published results of some first error correcting codes where we've been the first group to show like real-time error correction in these kind of devices. Another way that you can use this feature is in quantum simulation. So this is a little bit of the flavor of the algorithm shown earlier, where you can kind of break a problem size down a little bit. But the basic idea is that if you think of a material like a 1D magnetic material, and you have these spins that are interacting with each other, they're necessarily kind of local interactions. And so the entanglement in a material is going to be kind of local. And using that fact, you can actually, this paper shows how you can simulate devices. This is a case like a 1D32 site system only using 9 qubits. And we got really great agreement. So the lines on the data on the right are the classical like theoretical prediction, and our data is kind of right on top of it, showing a spin excitation kind of moving left to right in the chain through time. So the time is on the y-axis in this case. And this really takes advantage of the fact that you can measure and reset just some of the qubits in the device while the rest of it stays in a quantum coherent state. So to talk about that, the other like demo I wanted to set up to do was the quantum teleportation circuit. Again, it's a really simple thing, but it takes advantage of this mid-circuit measurement idea. And one of the cool things about doing this demo with the ion trap is you really are going to be teleporting the quantum state from one side of the device to the other. So I've kind of laid the image of the ion trap suggestively next to the circuit. And the idea is that the quantum state that we want to teleport is going to be up at the top of the trap in qubit 0. And we're going to send it all the way to the other end of the trap, which is something about like 3 or 4 millimeters in real space. And so, okay, up at the top, that first gate is just doing some rotation. In principle, the real power of this protocol is that we don't know what that quantum state is, and yet you can still like make a copy and send it out. But so we'll prepare it, we'll pick a state to be sent. And then the other thing that this protocol relies on is you have to send 2 classical bits from one side to the other. That's kind of happening after the gray barrier in this case. But you also need to start with an entangled state pair or a Bell state pair. And so kind of the idea is in the middle of the trap, we have our entanglement factory. And so this Hadamard and C0 is going to create an entangled Bell state pair. And then those other lines actually represent sending that resource to the opposite ends of the trap. So one of the entangled qubits gets sent up to Alice, who's up at the top, and the other one is sent to Bob down at qubit 11, and that's the one we're going to finally read out at the end. So, and this really represents like swapping the ions through the trap to either side. So then Alice does another entanglement swap and measures the 2 qubits that we have on that side. And then the information from that measurement is going to get stored in some classical registers. And then in real time, we will conditionally perform the X and the Z gates on the final qubit before measuring it to like extract the copy that we sent. So that's the basics of the protocol. Now let's see if it actually works. Okay, so I'm going to stop sharing there again. I'm going to jump back to my notebook. We're just going to dive right in and see if we can connect to -2 right now. It's showing reserved. Oh, sorry.
Can you hear me now?
Yeah, you're right. That's not going to work very well. Screen sharing, stop sharing.
So we share this with you. He's actually logged this slide.
Okay, it should be sharing still on here. So, oh man, I know what I need to do. I need to stop the presentation mode, I think. Okay, I realized that I took too long and I ran out of our machine time reservation, but now I get to see what the simulator does. So from a from an interface side, it performs really similarly, and it's updated on a regular basis with the metrics from the real hardware. So try to give people like a really representative look at what it's going to be like to run on the hardware. Okay, so first I'm just going to try and transmit a 0 state across the device. So that's what I'm setting there. Then this is just creating the circuit that we were just looking at and walked through. Use the same kind of functions to submit it. Now, what I was actually finding is that the emulator is a bit slower than the real machine. I don't know if I don't think that's the actual computation is slower, but maybe just some of the network like latency pieces seem to be a bit slower. But that one was ready. So all I'm doing here now is plotting the states of the final classical bit. And if the protocol worked correctly, we should see that it's always in the 0 state. And so there you can kind of get a sense of like what kind of error that we're hitting here is like 38 out of 1,000 shots. Meanwhile, so if I go through and just delete these 2 conditional gates, what do you think we would see for that last qubit at the end? Yeah. So I'm sending that in with the conditional gates deleted. Now we're just measuring that, essentially measuring one of those bell pairs again. Okay, yep, so we're still waiting in the queue on the emulator. This is why people love the reservations. It's definitely the case like that, users typically would do a bunch of pre-work, use the emulator to kind of have a big package of circuits ready to go, and then would like dump the whole package in and let it run overnight and then come back to your data in the morning, as opposed to this like direct interactive mode. Anyway, it's been interesting to go back to this like huge era of computing again. It's quantum computers. So it did actually complete, and yeah, you see 50-50 without using the conditional measurements. And then we can put it in. So, we had that like 38 shots. If we had a target of trying to get 80% in the population 1 state, the initial rotation is going to be about 0.7 pi to make that happen. And then it usually comes in with the error like slightly below whatever you ask for in that case. I could just easily swap over to my talk. I could the next thing. How important is it that I stop at 3:30? Okay, I only have a few more slides. So just kind of talking about, what's next. All right, let's see here if it works. Yep, and so we were shooting for 800 here, got 776. Great. But yeah, so that's a little bit what I think probably this looks really familiar if you've used other sorts of tools for constructing quantum circuits, but it does give you access to this really powerful compilation suite that Cambridge Quantum developed, and it's open source for you to use, and you get to also take advantage of how easy it is to script up things in Python to write your circuits. Okay, so last couple slides. Where are we going with all this? This 12 qubit machine is really performing great. It's kind of like exceeding my wildest expectations, honestly. But 12 is not enough. We need to go to a lot bigger devices. Fortunately, we have work to do that. So one of the first steps is to break out of just this 1D QCCD geometry and go into 2D. And so to that extent, we've started fabricating devices with these, what we call these junctions. So there's a picture of that on the right. With the idea is that as we kind of perfect that junction design, you can go to these very large 2D grids of basically shuffling the ions all around and adding more and more qubits, but basically being able to keep a lot of our laser beam stuff the same, which you can see that's really pretty important because it's a big part of the system. So this is actually a device of a single ion moving through the junction. Is the video going to go? No. Oh, bummer. Ask me later. I can show you the video if you want to see it. But it's just, the dot appears in the center, the dot appears in the top, bottom, and left and right. And we're able to do this with like actually pretty low heating per round trip. So it's pretty exciting progress. And it's real critical to, the hardware roadmap where I kind of skipped over this, but the idea is the first step after the linear device is this racetrack device where you can kind of imagine stretching that linear around a loop and connecting it up. And it proved out some good microfabrication techniques. And the goal is to launch that thing this year with more qubits and really opening up some of these kind of quantum simulations in a realm where it really starts to compete with what classical computers can do. And then, the future is going to more and more of these grid architectures. And we've, I showed you the junctions. In the future, the idea is also to get some of those laser sources integrated into the devices themselves. And we're taking steps to do that as well. So another cool thing I want to make sure this group is aware of is there is access to the devices for research. Both Oak Ridge National Laboratory, they have a subscription and you can sign up through their website and get machine time through them. And Azure, we're on the Microsoft Azure Quantum Cloud. They have a credits program as well. So it's something you're interested in, check it out. I kind of told you this hardware really needs subject matter experts from a huge range of expertise, electronics, software, but also cryogenics, lasers, electronics, and we have job openings in all of those things. So it's really easy to go to our website, quantinuum.com, and go to careers and look at those, or you can talk to me. But I know I'm over time, so you to take questions later, or thanks. It's really fun to get to talk to you all. Let's see. Did you have a question?
Yeah. So I think one of the biggest time penalties is I think recooling the ions. Is that right?
It's definitely a big contribution.
I see. And do you have to recool after like a certain number of swaps or something?
No, we don't count swaps right now.
Okay.
They're low enough. I don't think we've really seen any circuits. I think you could potentially design some terrible circuit that because what we do is we recool before 2 qubit gates. And so if you had some circuit that did tons of swaps for some reason and no 2 qubit gates, which might be hard to actually design anyway, that's, I think, what's kind of keeping things. And then we do have additional Doppler cooling as well, which kind of protects from real runaway situations.
I have been also the presentation of my colleague Justin.
Yeah, go ahead.
So or with quantum compiler package, right? Like you have to have the different architecture as well as the non-termism and correcting, or they use custom bricks and Jasper, which is so IR opposition asks assembly instruction. It's a bit of a specific one. So
yeah. Okay, so I don't have any expertise. I certainly don't have any insight into the high-level compiler that recognizes patterns in the quantum circuits themselves and can reduce gate counts.
Yeah.
I know a little bit more about then our ion trap specific compiler, but in terms of the details of GCC or intermediate representation passes, I just don't know those details. It is, I think, actually is maybe a provably like computationally hard problem to optimally sequence the gates and optimally do the transport. So I know the team is taking advantage of heuristics to kind of block circuits and do the best estimate that we can. Because you could imagine like this is a problem you have to tackle as the circuits get very large. The classical computer can't compile them fast enough to run them on the devices. And that's a problem. We're not there yet.
So I think you kind of touched on this a little bit, but to put it into context, if you have to say kind of the major differences in the trapped ion architecture in comparison to either other industry players that are doing trapped ion or the architectures that you suggested in academia, what would you say really and why that?
Yeah, I mean, one of the big ones is that right now we're the only trapped ion group that is really doing the transport in the devices. And that's not to say like, I think, we just, I think honed in on saying like, this is a great problem for us to tackle right away and try to work on that. We kind of saw it as one of the hardest steps to do. And I think we just also saw an opportunity that it would kind of place our device nicely for researchers who want to study the error correction algorithms, because it would open up this mid-circuit measurement and reuse by getting the other ions away. So I think that's probably the biggest thing. And then it does have the advantage because our 2-qubit gates don't have the other ions around from those operations. They're higher fidelity. And so I think that's letting us get to deeper circuits demonstrated by the quantum volume metric.
So if I understand correctly, you use like hyperfine splitting phenomenon to why do you choose to do that instead of an effect on the atomic scale that perturbates the energy levels more? I don't know. Is it just convenient for this particular design?
This feels like a grad school comps question. I think that the energy scale of the splitting is one of the reasons why the excited state actually has a really long lifetime. So some quantum computing groups in academia do use like a transition to the p orbital as their qubit. And there's atomic selection rules that mean that decay channel is also pretty protected. And so that qubit can also have long coherence times in that excited state. But the hyperfine is just, it's like, it's measured not in like minutes or anything. It's like many thousands of years, I think. So I probably can't give a better answer than that. It is very convenient that the energy scale is like about 10 or 12 gigahertz, because there's a lot of great microwave electronics that we can take advantage of and use to also track as our qubits, much like the superconducting groups do.
Yeah, plus the interaction between the spin of electrons.
And that hyperfine state does, the details of it does mean it has some first order insensitivity to magnetic fields. So that being said, magnetic fields are like one of the worst things that we fight in the lab, but it is better than some other qubit choices you could make.
So you require a shell state and you also require 2 small states. Wondering if requires physically small qubits and the small state also small. What I would imagine it would be much easier and less costly to physically qubits.
You're totally right. It was a contrived example that I thought was kind of cool to show, but that's exactly right. So the great thing about the ion trap is if you wanted to send Q0 to Q11, you could just swap it through the device and have like basically perfect fidelity. And that would work much better than doing this. So it is, it's still, I think, of interest in cases where you really think about very remote information sharing, and you'd actually have devices connected by quantum networks. or at least connected by Bell state pair factories. Then that's actually a much probably easier problem to solve than a full quantum network, right? If you could just have two trusted partners that are getting Bell state pairs and then sending classical information to each other. So it's a contrived example. Yep. So the publication on fault tolerance, we kind of went through where we thought we had to get to be at kind of a pseudo threshold where the actual, logical qubit would be outperforming a single qubit. And it looks like we needed to reduce the 2 qubit gate errors by about a third. So definitely some, that's not going to come easy. But there was 2 other sources of errors that we had to reduce more. One of them was decoherence from the fluctuating magnetic fields. And we think we have really good, a good handle on that one. And so that needed to be reduced by about 10x. But, we actually think that that one's not going to be an issue. The other one that needed to be reduced by a significant amount was if I go all the way back to the beginning, I showed kind of that hyperfine energy level structure, and there was 2 states that were labeled as the qubit states. But sometimes when you're doing these laser operations, a qubit can leak into those outer wing states, and we call those leakage errors. And so we need to implement some additional laser pulses that will fix the leakage errors. And so that way, because they're a real problem for error correcting codes, because it doesn't show up as an error in the code. It shows up as kind of like the qubit is gone, or it just like doesn't work at all, and it just trashes the whole thing. So with these leakage correction, you can pump the qubit back into the qubit manifold, and then it will show up as an error in the detection, the correction circuit, and you can fix it. And so those are 2 key things that we need to do going forward to keep making progress in the error correction front.
One of the feature models, I think it was H3, one of the key enabling technologies that you have to see there, scale control systems.
Yeah. It's really talking about the H1 device has, I think, like 250 electrodes or 250 independent signals. We just kind of control them all. The future devices are going to have many more electrode patches. And so you have to figure out how to broadcast your control signals and not need to have every electrode individually controlled. So it's kind of solving some of those problems.
This might be a stupid question. So for quantum, how do you think it will scale when like the number of qubits?
Yeah, that's going to be a great problem to have. Yeah, I hope we find out really soon. I'm not sure. I think you have to find a different benchmark.
I think there's a question.
Oh yeah.
So can you talk about recent results with the BA137 and where you go?
So yeah, we recently put a paper on the preprint server where kind of our R&D groups demonstrated using a different qubit. So I mentioned barium-138 as doing just the cooling, but there's a different isotope, 137, that actually you could use as a qubit, and it would have a lot of the nice properties of the ytterbium qubit, but the lasers get a ton easier. Like you can use, yeah, it basically just moves closer to the infrared and telecom wavelengths. And yeah, there's a lot of good reasons that it would help. The problem with barium-137 is that hyperfine structure is a bit more complex. And so previously teams had not been able to prepare a pure initial state. And so if you can't start with a good pure qubit state, then the rest of your operations aren't going to be as good. So we kind of developed a scheme using a series of laser pulses or microwave pulses to do that kind of quantum state purification. And then the team then used that pure state preparation and demonstrated reading it out at kind of like a world record fidelity of 0.9999, 4 nines basically. And so that's actually an important step on the error correction roadmap, because if you keep improving the 2 qubit gate fidelity but don't improve your measurement, that's going to become the blocking point in doing the error correction code, because you might do all the gates right, but then make an error in your measurement, and then you correct the wrong error and insert a new one. And so the measurement also needs to kind of keep progressing on that roadmap as well. So the good news is I think we're really optimistic about inserting that new qubit soon, because a lot gets to stay the same. We're already working with ytterbium and barium as the ions in the trap. We have the lasers for them. So I think this is not it's not an H5 development. I guess I'll say that. It's like, we think it could be inserted soon. Not in the H1 devices, because they kind of you have to pick what species of ions you're going to work with as it's assembled. So another question?
I guess the bandwidth spheres are kind of proportion, which they are like so the second of the net cost of
yeah, so I think what you're asking is, when you do the swap and you're kind of pushing the ions off of that line, do they get excited by the RF micromotion, which is kind of an effect in ion traps? So they do experience that micromotion, and that's one of the reasons why in that picture, as it's doing the swap, they get brighter, because it actually, the micromotion causes them to shift closer into resonance with the laser beam. But we can do the swap in a way that excitation is pretty coherent and doesn't leave like energy behind in the chain. So you can definitely do the swap wrong, and it does heat up the ions, but been able to kind of do the studies on that to find the right rotation waveform that keeps the crystal cold at the end.
Do you have any barriers to overcome, or how do you connect it?
It's an energy barrier. I don't know the details about an energy barrier in the junction. I know that it is not perfectly smooth, and there's actually some finessing of how ions transport through the junction that you have to take into account to make sure that you don't heat them up moving through. There's like a pretty specific waveform that we kind of found to move them through the junction and through some of the kind of violent stuff that happens in the electric field environment to come out on the other end with low heating.
Thank you for a very interesting talk. Regarding the quantum volume, you mentioned that it's one of the bench metrics or the benchmark, although there are some issues with the error issues. So where do you see a metric that will be able to, across the board, enable comparisons? Like in the HPC world, we have LINPACK, and at least for a long time it was LINPACK, and it's evolving. So that will be able to make some sort of comparison about sustained performance. So how do you see, where? Because I understand IBM is pursuing something else, and there seems to be like multiple standards.
I guess I think quantum volume is pretty good right now for if as a cross-platform heuristic of how is kind of any given circuit going to perform without some maybe really specific error mitigation techniques. how is it going to perform? And so in that sense, I think it is maybe the closest we have right now to this kind of broad purpose benchmark. You mentioned IBM. So like quantum volumes started with IBM. And I think they've now been talking about, they also want to capture the speed. So, okay, you have the dimension of how many qubits, how deep of circuit, and how fast do you actually accomplish that circuit. And that's what they call like the circuit layer operations per second, or CLOPS, which I think is, yeah, it's important to understand like the wall clock times. And that is not captured in just the raw quantum volume number. So I think that's a good way to go. But in terms of understanding, like, you give me one number about a device and have some general sense of how deep of circuit I'm going to be able to run, I think quantum volume is pretty good right now. It runs into the problem of when you get into the quantum advantage regime and you can't do the classical calculations anymore, then I'm not sure. So that's kind of my take right now is I think quantum volume is pretty good at predicting how a device is going to perform. Although that said, there are definitely specific applications that have real structure to them that just say, you could say this kind of performs bad on all this random rearrangement, but on this one specific application, it might still be pretty good. Say a circuit that only had nearest neighbor interactions, for example. A superconducting device might perform worse on a quantum volume test, but still be able to do pretty good with all local interactions. And I think actually the racetrack device could be a little bit in that category because there's a lot of transport moves that you have to do arbitrary pairing in that device. But to say, take a few of the qubits and just interact them with their nearest neighbors, you can do those transport moves pretty fast. And so that's one of the reasons I think we're interested in using some of these quantum simulations where you're looking at Hamiltonians that are smaller dimensionality, but still classically hard. Maybe we'll, yeah, anyway. I don't know if that's a good answer. I think the two reasons are we really want to solve, we don't want to solve the electrode scaling problem and the optics problem in one generation. It's kind of like you'd like to have, sort of, like being able to take kind of steps in engineering and yeah. It's priority. I think we can make some exciting devices by doing the grids first without the optics. And I mean, I think the optics are really hard too. So I think they need more time. Thanks. This is really great. Should I go ahead and sign off?